Welcome, students. We are now heading towards glucose degradation in the cell, starting with glycolysis. The definition of glycolysis is breaking down monosaccharides, which includes glucose, fructose, and galactose, to 3-carbon pyruvate. The interpretation of glycolysis would be split sugar, meaning split monosaccharides to 3-carbon pyruvate, or lactate. Glycolysis provides energy to nearly all living organisms under both aerobic and anaerobic condition, although the quantity of energy produced only from glycolysis is very limited. This pathway happens in cytosol and produces a substrate such as pyruvate to generate more energy under aerobic conditions in mitochondria, or lactate under anaerobic condition. The total energy produced only from glycolysis is 2 ATPs. Glycolysis is comprised with two phases, one with energy spending and the other with energy generating phase. During the first phase, 2 ATPs are used to activate substrates, and 6-carbon monosaccharides are eventually split into 2 triose phosphate. During the second phase, the total 4 ATPs and 2 NADH units are generated, and under aerobic condition, NADH would further be oxidized in electron transport system, and pyruvate would go to Krebs cycle, which will be covered in the following module. Under anaerobic condition, NADH will be used to convert the pyruvate to lactate. Let's take a look at each step more specifically. During the first energy-consuming phase, low-energy substrates such as glucose should be activated to glucose 6-phosphate by either hexokinase or glucokinase using 1 ATP. Then glucose 6-phosphate is isomerized to fructose 6-phosphate and further phosphorylated again to generate fructose 1,6-bisphosphate using second ATP. Fructose 1,6-bisphosphate is split into dihydroxyacetone phosphate and glycerolaldehyde 3-phosphate. They are interconvertible and both contains phosphate groups from each ATP. Other monosaccharides are also following very similar pathway to glucose. Galactose is phosphorylated to galactose 6-phosphate by galactose kinase, and galactose 6-phosphate is switched to glucose 1,6-phosphate by UDP glucose from glycogenesis. Further isomerization process produces glucose 6-phosphate. In liver, galactose can be converted into glucose 6-phosphate through this mechanism, and glucose 6-phosphate can turn into glucose by glucose 6-phosphatase during the glycogenolysis in liver or glycolysis process to produce energy. However, in muscle, only glycolysis pathway happens. Fructose can be converted directly to fructose 6-phosphate by hexokinase, which is only preferred when people are deficient in glucose. Mostly fructose is phosphorylated to fructose 1-phosphate using first ATP and then further metabolized to dihydroxyacetone phosphate and glycerolaldehyde 3-phosphate using second ATPs. Whichever monosaccharide is used in glycolysis, 2 ATPs are consumed to generate glycerolaldehyde 3-phosphate for next phase. The key enzymes to control the first phase include hexokinase, glucokinase, phosphofructose kinase 1, and fructokinase for fructose. All these are involved with increasing the energy level of substrate. Second phase for the energy reduction starts with glycerol 3-phosphate. The first step involves with phosphorylation, but adding a free phosphate to number 1 carbon without using ATP and oxidizing it by taking 2 protons. During this oxidation process, aldehyde becomes acid. Redox reaction happens when electrons or protons are exchanged, so substrate is reduced by receiving electrons, whereas another substrate is oxidized by giving off electrons or protons. In this case, nicotinamide adenine dinucleotide is reduced by receiving a proton, while glycerol aldehyde 3-phosphate is oxidized. After receiving another phosphate group, 1,3-bisphosphate glyceride is under a high energy state and it is able to donate 1 phosphate to ADP. This process is called substrate level phosphorylation, which is easy but inefficient way to generate energy to ATP compared to oxidative phosphorylation through electron transport system, which will be covered in the following modules. The following reactions of isomerase and dehydrogenase will produce another high energy containing substrate, 2-phosphor-N-pyruvate, and another substrate level phosphorylation to create another ATP. Remember, this phase will happen twice because 2 glyceraldehyde 3-phosphates are generated during the energy consuming phase. So a total of 4 ATPs from this phase are generated. If glycolysis is the only reaction to energy production, net production of ATPs will be 2 ATPs because 2 ATPs are already consumed during energy consuming phase and 4 ATPs are generated during energy production phase. Final product, pyruvate, is an alpha keto acid, which is very versatile because it can be easily converted to amino acid, which is called alanine, lactic acid, acetyl-CoA for fatty acid synthesis, and back to glucose. We'll talk about this integration of all macronutrients in the later module. Here are some differences between aerobic and anaerobic glycolysis. NADH produced during the glycolysis will be removed to mitochondria, where its electrons are donated and used to produce more energy in electron transport system under oxidative state. Another fate of NADH is happening when oxygen is unable. The fate of NADH is be recycled and oxidized and reduce pyruvate with alpha keto acid to lactate, which has hydroxyl acid. Lactate is usually built up where oxygen supply is limited, lowers pH, and cause cramps in muscle after exercise. Lactate can be converted back to pyruvate depending on the availability of oxidized NAD. Key regulatory enzymes in the second phase include phosphoglycerol kinase, pyruvate kinase, which is a regulatory enzyme, and lactate dehydrogenase. Through this module, we learned the initial substrate, glucose, fructose, galactose, and the ending substrate, pyruvate under aerobic, and lactate under anaerobic condition during glycolysis that has energy consuming and energy generating phases. Key enzymes include glucokinase, hexokinase, fructokinase, and phosphofructose kinase during first phase, and phosphoglycerate kinase, pyruvate kinase, and lactate dehydrogenase during second phase. Thank you for listening.